Hello, I am Strange DNA, and today I will be analysing the famous cinematic marvel, the B movie. Obviously, this is a very in-depth and realistic movie. Quite the documentary about bees. Actually, it's it's very very good, and if you haven't already watched it, I would strongly suggest doing so. But today we'll be analysing it a bit further than it perhaps was intended to be. So let's go on to the first question. Why do the bees look so cartoonish? If we check a picture of a bee according to science, we can see that it does differ quite a lot from a picture of the bee according to the Bee movie. So, obviously, since the movie was filmed using high-tech cameras, the close-up shots would look very detailed. Clearly, our eyes don't have high-tech lenses, so we probably just see something depicting the scientific image. But the cameras do have high-tech lenses, so they can take much clearer videos, meaning they'd probably look like the more cartoon image. I was just looking into the cameras used for the filming, and they're not revealed openly, so I had to look at some news interviews. And according to the source on Google, where some people interviewed DreamWorks Animation, they found out that they used this camera, which, as you can see from that photo, quite looks very realistic. So clearly, it would be able to take much better pictures than our eyes could. So the conclusion then is that Barry B Benson and his fellow bees appear cartoonish on camera due to the high-tech lenses used to film, which are absent in our eyes. Question 2. Why is Barry not really squeaky? The larynx, more commonly known as the voice box, is what allows animals to make a vocal noise. According to science, bees don't have voice boxes, but science also thinks bees shouldn't fly, so should we really trust science on this one? Let's say that our bees do have voice boxes. The length of your vocal cord stored inside your larynx determines the pitch of your voice, so let's find out how Barry B Benson actually sounds. We need to know how big his larynx is. Measurements. An average larynx in a human is about 5 centimeters long, but how wide is it? The diameter of a neck is about 12.095775675 if we divide 38 by pi. This image gives us a picture of the larynx covering roughly 4 times the human neck by diameter, giving us a diameter of around 4.838310269999 centimeters. Multiplied by the initial 5 centimeters gives us 24.19155153 centimeters squared. Now, for the third dimension, the image below shows a larynx covering roughly 1/3 of the diameter of a human neck. This equates to about 4.031925222499 centimeters. This multiplied by 24.19155135 gives us 97.5385261198 centimeters cubed. Weight. The average human body weighs 1 gram per cubic centimeter. Therefore, our larynx weighs about 97.5385261198 grams per centimeters cubed. Since an average person weighs 62 kilograms and is 62,000 cubic centimeters, the larynx is only 0.00157320203% of a person's body weight. How heavy is Barry B Benson's larynx, though? A typical honeybee weighs about 0.00011 kilograms. If we multiply this by the percentage we worked out earlier, we get around 0.0000001735052 grams, or 0.000173052 micrograms. How big is Barry B Benson's larynx? Weighing in at 0.0001 kilograms, this means that B's larynx would only be, that was a very good joke obviously, 0.00000015732 of a bee's body weight. A bee is about 0.63 cubic centimeters in size, meaning that a bee's larynx would only be 0.000000000991116 cubic centimeters. If we use the ratio from before, which is roughly 5 to 5 to 4, meaning there are 14 parts in total. To get the height of the larynx in Barry, this being one of the 5s in the ratio, we get a height of about 0.0000000003539 centimeters. Pitch. An average human male's vocal cords are between 17 and 25 millimeters long. An average male speaks at around 85 to 180 hertz. There is a difference of 8 centimeters and 95 hertz, which means that we can calculate for every millimeter your voice changes pitch by 11.875 hertz. Barry B Benson's vocal cords are 0.000003539.7 millimeters long. The difference between that and the 17 millimeters with 180 hertz is 16.9999964,603 centimeters. This multiplied by 11.875 gives us 203.787457568, plus the 180 from the original 17, and we get 383.787,457,568 hertz. For reference, the higher end of the female spectrum is about 255 hertz. True voice. Define Barry B Benson's true voice, and we need to scale the audio of him speaking. By analysing a clip from the film, we see that Barry talks at around 163 hertz. The pitch changer I use measures in semitones, approximately 1.06 Hz each. This means I need to add 234.034705022 semitones to the clip. After messing around in Audacity, I finally managed to get it to 384 Hz, an approximate of our number from earlier. The reveal. Ladies and gentlemen, I like to reveal to you my approximation of Barry B Benson's voice. Conclusion. Although his voice would probably be a lot squeakier, it still proves the point that they must have used a special microphone in the movie to hear the bees. After all, it is a documentary with real bees. Question 3. How quick is the bee car? If you were paying attention, in the beginning of the movie, Barry B Benson and his counterpart Adam Flamen are seen driving in a bee car. I will now attempt to find the speed of said car. Houses per second. To find out how quickly the car is travelling in the scene, I need to work out how many houses it passes per second. In one shot that we can see, it takes around 2 seconds to pass one house, so that's half a house per second, or 0.5 H per S. Now we need to find out how big a house is. Bee houses. To work out how big a bee's house is, we need to know how many bees per cubic centimetre. So how big is a beehive? We know that they are usually around 19 times 9 times 16 inches. So then we can work out that they are about 6,949.44 cubic centimetres. Bees are around 0.63 centimetres, so we assume that a house is for a family of 4 bees, then they may need around 5 centimetres cubed of space for each house. This does mean that the proportions shown in the movie are slightly off, but this could be due to the high-tech lens previously discussed, which may have led to some scaling issues during rendering. If we assume the houses are cubes, we get a length of 1.3 centimetres for the front of the house. Conclusion. If we know that the front of the house is 1.3 centimetres, then a H per S would be 0.65 centimetres per second. This means that the bee car travels around 0.65 centimetres per second, or 0.0065 metres per second. To put this into human road terms, a bee car can travel at 0.0234 kilometres per hour, or 0.01454,009 miles per hour. Number 4. How strong is Barry B Benson's stinger? The fight. In the Bee movie, there is a scene where Barry B fights a shop worker, Hector, who wields a board pin against Barry's stinger. To find out how strong his stinger is, we just need to know how much pressure it can withstand. Pressure. To calculate the pressure placed on Barry's stinger, we need force times area. Force. Let's start with force. Force is measured in newtons and is calculated as mass times acceleration. A human hand and forearm weigh about 2.295 kilograms. Then we need to find acceleration. Acceleration is measured in meters per second squared. A human hand can travel at 100 miles an hour, or 44.704 meters per second. This is our final velocity. To find this, we need the initial velocity, 0 meters per second, final velocity, 44.704 meters per second, and the time, about 0.2 seconds. We substitute this into A equals V minus U over T, and we find the acceleration is 298.0267 meters per second squared. Then we put these numbers into F equals MA and get a force of 683.9712 newtons. Area. Now let's work out area. To find the area of a board pin that came into contact with Barry B Benson's Singer, we need to work out the area of the pin. A pin is about 1 millimeter in diameter, so using C equals 2 pi r, we get 3.14159 millimeters as circumference. Then we can multiply the length of the pin, about 12 millimeters, which means we get an area of the pin is about 37.69908 millimeters squared. Then repeat this process with Barry's Singer. A 0.057 millimeter diameter means a circumference of 0.35814 millimeters. The length of the stinger is about 1.5875 millimeters, so we have a total area of 0.56854,725 millimeters squared. Then we rotate these perpendicular to each other as they are crossed in the movie. This means that we need the circumference of each multiplied. This is 1.1251290,426 millimeters squared, but let's half this to offset the curvature of both objects. 0.562564521 millimeters squared is our new number and the area. Now that we have both force and area, we use the formula P equals F divided by A and find out that the pressure is 1,250,809,341 pascals. Conclusion: steel can withhold 250 million pascals, which effectively means that Barry B Benson is almost 5 times stronger than steel. Question 5. How did the bees carry a plane? The plane. In one scene of the Bee movie, we see a commercial airliner being lifted by a swarm of bees. Furthermore, the bees are able to generate enough reverse thrust to be able to fully stop the plane from cruising speed. This is important to work out how strong each bee will be to lift such a weight and find out how they generate such a reverse thrust force. The formula. To calculate the force at which the plane is being pulled by one bee, we need a formula that goes something like this. F of 1b equals m times v minus u over t over total bees. Deceleration. Let's start with deceleration, the v minus u over t part of our formula. The plane travels at a cruising speed of about 900 kilometers an hour. Now in the movie, the bees go from full speed to stopping the plane in about 3 seconds. This means that v equals 0 meters per second, u equals 250 meters per second, and t equals 3 seconds. This gives us an acceleration of minus 83.334 meters per second squared, or a deceleration of 83.334 meters per second squared. Heavy. For the following calculations, we need to assume that the aircraft is a Boeing 747 airliner. The 747 has a weight of 412,000 kilograms when it is full of fuel and passengers. The plane would probably be on about half a tank by the time it arrives, though, so its weight would be reduced to 318,500 kilograms. To find out the total amount of bees, we need the area of the plane divided by the sides of a bee. The diameter of a Boeing 747 is 6.5 meters, and the length of the fuselage is 68.83 meters. So pi times 6.5 times 68.83 divided by 2 is 702.766422626 meters squared. Obviously, the bees cannot fit around some areas of the fuselage, so this is balanced out by the tailplane. Then we just need to add the area of the rings, 541.2 meters squared for both, to give us the total surface area of 1,243.966422626 meters squared. Then we need the surface area of the top of a bee. We know that a bee is around 0.63 centimeters cubed, and they are about 10 millimeters or 1 centimeter tall. This means that the top of a bee is 0.63 centimeters squared, or 0.000063 meters squared. So now we divide our plane surface area by the bee surface area, get that the total amount of bees is 19,745,499. The answer. Now that we have the 3 main parts of our formula, let's add them in above. So the force of 1b is 318,500 times 83.334 over 197,45499. This is equivalent to 26,541,879 divided by 19,745,499, or 1.34419894883 newtons. Conclusion. According to our estimates, A bee weighs around 0.00011 kilograms and can lift 50% of its own body weight, so 0.00055 kilograms. This is then equal to 0.005393658 newtons. This means that I have proved once again that humans know nothing about bees, and that they are about 2,492 times as strong as we previously thought they were, which pretty much means that if you see a bee, you're completely screwed. Run for your life. And that is the end. If you have enjoyed this theory video and you want to see more stuff like this, check out the playlist that I probably linked in the description if I remember to. It is, of course, a lame theory. We've got some other stuff on there, like a theory on the Lorax, theory on KFC. We got one on Dwayne Johnson as well. That one underperformed a tiny bit, although I think it was quite good, so you should go and give it a watch if you want. But here we are at the end of our theory video. Thank you, and goodbye.